In this example, we are going to determine the potential energy of this system of four charges. There are 4-point charges located at the corners of a square of side length 2 meters, and the charges themselves are given in the problem. The question we are effectively asking is, how much work does it take me to assemble this system of particles? To answer this question, we will have to build the system of particles. So in doing that, we will assume that initially none of the particles are in their final configuration as shown here. So we're going to remove all the particles, and we will assume that all of these particles are initially infinitely far away from the square. We will reach out one at a time, bring one particle and place it into position. And when we do that, we will calculate the change in potential energy when we place the first particle. Then we will reach out, place the second particle, calculate the change in potential energy when we place the second particle, reach out, place a third particle, calculate the change in potential energy in doing that, and the fourth particle. Then we could add up the total change in potential energy. At the end of this video, there will be a subtle distinction between the work we do, the change in potential energy of the system, and so on. We'll address that when it comes. So let's think about what we have. Initially, we have empty space, and we have the 4 particles that we want to place. They are currently infinitely far away. So what I'm going to do is I am going to reach out to infinity and place the +2 microcoulomb point charge first. It really doesn't matter which charge we begin with. So I reach out to infinity, and I will pick up the +2 microcoulomb point charge and drag it and place it right here. We have placed the +2 microcoulomb point charge into its final position. Now we will calculate the change in potential energy of the system in placing this first charge. So I will use this equation. At present, the other 3 charges that we are eventually going to place are all infinitely far away from each other. So initially, this +2 microcoulomb point charge was infinitely far away from the other charges. And when I look at the electric potential due to a point charge, I have V equals kq over r. As r goes to infinity, the value of the electric potential will go to 0, because I essentially have a finite number divided by infinity. So I could say at the initial position of the +2 microcoulomb point charge, V initial is going to be kq over infinity, which is just equal to 0. And at the final position of this point charge, the electric potential due to the other charges that I did not move is going to be V final is also equal to 0. Because again, these 3 other charges are infinitely far away. So I would say the change in potential energy in moving the +2 microcoulomb point charge will be equal to the charge of the particle that moves. So that'd be 2 times 10 to the -6 times 0 minus 0. And so the change in potential energy moving this charge is going to be 0. I will call this delta PE1, the first charge that we moved into place. Now that we have moved our first charge into place, we will move the second charge into place. As I said before, it doesn't matter what order we place the charges in, we will get the same result at the end of the day. So I'm going to now choose to move the +1 microcoulomb point charge from infinitely far away to its final position right here. So let's see what we get. Initially, the +1 microcoulomb point charge is infinitely far away, so it is way over here. But then we drag it and we place it right here. So here is the +1 microcoulomb point charge. Because the +1 microcoulomb point charge begins infinitely far away from all the other charges, I could say the value of the electric potential at this guy's initial location is going to be 0. But now, because there is another charge in the vicinity of the final position of the +1 microcoulomb point charge, the value of the electric potential right here is not going to be 0. I would say V final at the final location of the +1 microcoulomb point charge is going to be equal to Coulomb's constant K, 9 times 10 to the 9, times the charge of the +2 microcoulomb point charge. Because remember, when we calculate V, V is created by the charges we are not moving. So here I will have 2 times 10 to the -6, and then the square is a side length of 2 meters, so divide by 2. When I put this number through a calculator, I get V final is going to be equal to 9 times 10 to the 3, or 9,000 volts. So I could say that the change in potential energy in moving this +1 microcoulomb point charge into place would be written as delta PE is equal to the charge of the particle that moves, 1 microcoulomb point charge, so that will be 1 times 10 to the -6, times V final minus V initial. V final is 9,000, V initial is 0, so I'll have 9,000 minus 0. And I could say the change in potential energy of the system will therefore be 9 times 10 to the -3 joules of energy. So in placing the second charge into its final position, we have a change in potential energy of 9 millijoules. So here we will have 9 times 10 to the -3. We will now move the -3 microcoulomb point charge from its initial position infinitely far away from all the other charges to its final position in the upper right corner of the square. Just like before, because the -3 microcoulomb point charge is initially infinitely far away from all the other charges in this problem, the value of the electric potential at infinity is going to be 0. So we reach out, we grab that -3 charge, we drag it to its final position in the upper right corner of the square. When we ask what is the change in potential energy of the system in moving that -3 microcoulomb point charge into place, we know the initial value of the electric potential is 0 at infinity. We need to know what is the value of the electric potential in that upper right corner of the square due to all the charges that did not move. Now, when we moved this -3 charge into place, we had 2 charges that were stationary. The +2 and the +1 charge were both stationary during this move. So the +2 and the +1 charge will both contribute to the electric potential in the upper right corner of that square. I could symbolize that by writing V final is equal to the electric potential due to the +2 charge in the upper right corner plus the electric potential due to the +1 charge in the upper right corner. To find the total electric potential, I add the contributions from each of the individual charges themselves. These will be the electric potential due to a point charge, so I will again use V equals KQ over R. So I could say V final is equal to KQ over R for the +2 charge. We have K, Coulomb's constant, 9 times 10 to the 9. We have a 2 microcoulomb point charge, so that is 2 times 10 to the -6 coulombs. And this charge is 2 meters away from the upper right corner of the square, so I'll have a 2. And then I have the +1 microcoulomb point charge. So I would say Coulomb's constant K again, 9 times 10 to the 9. Then I have a 1 microcoulomb point charge, 1 times 10 to the -6. But now, because the lower left corner of the square is opposite the upper right corner of the square, this charge is going to be a distance 2 square root of 2 meters away from the final location of that -3 charge. So I will say 2 square root 2. Opposite corners of a square, you could use a Pythagorean theorem to find this length. So when I add up all of these terms, I find the final value of the electric potential at this location is going to be 12.3 times 10 to the 3 volts. Now I have enough information to find the change in potential energy when we moved this minus 3 microcoulomb point charge into place. I could say delta PE is equal to the charge of the particle that moved was the minus 3 microcoulomb point charge, so I will have minus 3 times 10 to the negative 6, and then I have V final minus V initial. So I will have 12.3 times 10 to the 3 minus 0. And when I put these numbers in a calculator, I get the change in potential energy is going to be negative 36.9 times 10 to the negative 3 joules. At this point, I am going to pause and say it is very important that we always keep the sign of the charges when we plug in numbers for Q and for delta V. If we have positive charges, we will have positive numbers. If we have negative charges, we will have negative numbers. The change in potential energy could be positive or negative. So I found a change in potential energy of negative 36.9 times 10 to the negative 3 joules. We have one last charge that we need to move before we have assembled our configuration of 4 charges in a square. Just like before, the initial position of the plus 4 microcoulomb point charge is infinitely far away from all the other charges, so I could say the electric potential, due to all the other charges, will be 0 at the initial position of that plus 4 microcoulomb point charge. We reach out to infinity, we grab that plus 4 microcoulomb point charge, and we drag it into its final position on the lower right corner of the square. In order to calculate the change in potential energy of the system, again, Q in this equation is the charge of the particle that was moved. So Q will now be plus 4 microcoulombs. And the electric potential, V, is calculated due to the charges that were not moved. Now we have 3 charges that were not moved, the plus 1, the plus 2, and the minus 3 microcoulomb point charges. We said that V initial is equal to 0 because the plus 4 charge begins infinitely far away. But when I calculate V final, there will be 3 contributions to the electric potential at the final location of the charge that moved. There will be the contribution from the plus 1 charge, the contribution from the plus 2 charge, and the contribution from the minus 3 charge. So I will have 3 terms of KQ over R because I have 3 point particles all contributing to the electric potential at that location. So the electric potential due to the plus 1 microcoulomb point charge will be Coulomb's constant K, 9 times 10 to the 9, times the charge of this particle, so 1 times 10 to the negative 6, divided by the distance from this particle to the lower right corner of the square, which is 2 meters. Then I will have the contribution from the plus 2 microcoulomb point charge, 9 times 10 to the 9, 2 times 10 to the negative 6. And because this is a square of side length 2, and we are considering opposite corners of the square, the distance between the upper left and the lower right corner of the square will be 2 square root of 2 meters. So I will have a 2 square root of 2 in the denominator. And then I have the contribution from the minus 3 microcoulomb point charge. So K, 9 times 10 to the 9, times the charge of the particle, negative 3 times 10 to the negative 6, divided by the distance between the upper right and the lower right sides of the square, which is 2 meters. When I plug these numbers in a calculator, I find that the value of the electric potential at the lower right corner of the square, due to all of the charges that did not move, is going to be V final equals negative 2.6 times 10 to the 3 volts. We now could calculate the change in potential energy when we moved the plus 4 charge into place. So I could say that the change in potential energy, delta PE, is going to be charge of the particle that moved, 4 times 10 to the negative 6, V final minus V initial. Remember, sign is important. We have a negative value for the final value of the electric potential. That's okay. I have negative 2.6 times 10 to the 3 minus 0 for V initial. When I put these numbers in a calculator, I get the change in potential energy is going to be negative 10.4 times 10 to the negative 3 joules. So we have a change in potential energy of negative 10.4 times 10 to the negative 3 joules when we move the final charge into place. We have moved each particle from infinitely far away into its final position in the specific configuration of charges, and we calculated the corresponding change in electric potential energy as we moved each particle to its final position. We found that there was zero change in the electric potential energy when we moved the first charge into place, and there was a non-zero amount of change in electric potential energy when we moved each subsequent particle into place. This should be reasonable to expect. If there are no other charges in the vicinity of a charge that we move, then there's nothing pushing or pulling on it. So there should be no change in electric potential energy as we place that first charge. But when we place the second, third, and fourth charges, there will now be other charges in the neighborhood pushing or pulling on those new charges that we're moving. So there will be some non-zero change in electric potential energy. We could then calculate the total change in electric potential energy by adding up all these contributions, and when we do that, we find the total change in electric potential energy in assembling this system of charges will be negative 38.3 times 10 to the minus 3 joules. So now we are going to move on to a fairly subtle part of this discussion. What does this number really represent? Let us imagine that the charges are going to begin and end at rest. So let's think about how we are assembling this system. The charges initially are infinitely far away. They are at rest. We reach out, we grab one of those charges, we move it into place, and we let go of that charge with that charge at rest. Then we reach out, we grab the second charge, we let go of that second charge at rest, and we do that for charge number 3 and 4. If that description does not really sit well with you, if you want to say, but as soon as we let go of the second charge, the first and second charges will attract or repel each other while we are grabbing the third charge, you could perhaps imagine that we are allowed to reach out infinitely fast, grab the third charge and place it, and the same with the fourth charge, before the other charges really have any time to react with each other. So by the time we have placed the fourth charge, none of the other charges are really able to move yet. The question as it was written asks, what is the potential energy of this system of particles? Remember that potential energy is an energy associated with particles' locations. If I think about a specific system of particles, we have to build that system of particles. In other words, we reach out to infinity, we have to assemble the system. The act of moving particles around requires me to either give energy or take energy away from those particles in ensuring that those particles arrive from infinitely far away where they began to their final location. Now, let's ask the question, when we were building the system, what were the forces acting on these particles? There were two forces acting on the particles. There was the Coulomb force, the force of electric attraction or repulsion, and there also was the force of my push as I moved the particles into place. So if I want, I could say as we were building the system, we were doing work on the particles. I could say the net or the total work done on the particles was the work done by my push plus the work done by the Coulomb force. We also said that we will assume the particles begin and end at rest. That point was important because that allows me to say the total change in kinetic energy of the particles before they were placed and after they were placed was 0. the particles begin and end at rest, they had no change in their kinetic energy. And from the work kinetic energy theorem, I could then say W net equals delta KE equals 0. This implies that the work done by me in pushing the particles around to move them into their final position will be equal but opposite to the work done by the Coulomb force. Now think back to when we talked about the work done by a conservative force. We could say the work done by the Coulomb force will be the opposite of the change in the electric potential energy. So I could say the work done by the Coulomb force is going to be the opposite of this number. So the work done by the Coulomb force will be plus 38.3 times 10 to the minus 3 joules. And this implies that the work done by me will be negative 38.3 times 10 to the negative 3 joules. If I think of the energy of a system as the amount of energy I need to give or take away from a system in order to assemble that system from all the particles' initial positions being infinitely far away, I could say that the energy of that system will be the amount of work it requires me to build that system. I said before, you could think of work as the amount of energy we give to a system. So if assembling this system requires me to do this much work, I could say that the total potential energy of this system is going to be negative 38.3 times 10 to the minus 3 joules.